Okay. Where's my full screen button? Here it is. All right. So today I wanted to introduce this concept of gradient descent. We're taking a little bit of a slight departure from what we were talking about earlier. So I guess in Monday's video, I had mentioned I think cross-validation as a way for us to kind of evaluate how well a model fits the data. We're going to take a slight departure from that for the time being, and introduce an optimization algorithm called gradient descent. Okay, the way we've been doing things as far as finding our parameters that minimize, our loss function or whatever, we've been using calculus, okay? So we've been saying we will pick the slope and the intercept that will minimize our loss function. Our loss function is the sum of squared error, or the mean squared error here, okay? So we're taking the difference between the actual and the predicted values. And what we said is we're going to calculate the gradient of our vector w, of the weights that we want to calculate, whether it's the slope and intercept, or if it's a polynomial, then you might have multiple weight values. And we did it using vector calculus, which simplified our notation, and we set it equal to 0, and we solved for it, right? And so you ended up with something like x transpose x inverse x transpose t, and things like that. Okay. There could be times where the loss function that we want to minimize might be even more complicated. And even if you could find the gradient, it might not be possible to set it equal to 0 and solve. Okay. So you might be able to find the gradient, but then setting it equal to 0 and solving for it could be tough, because especially if you're dealing with matrix notation, there's no division for matrices. You can multiply by inverses, but that only works for certain types of certain matrices, and so it can get tough, right? So we're going to take some computational approaches. Okay, now when we do this, it's important to note that we treat the data as fixed, okay? So the data has already kind of been generated, and now what we're doing is we have this function that's trying to minimize the differences between our estimate, okay? Our estimates and the fixed data points that we've gathered, okay? And so, so we treat the data as fixed. We're trying to find, the slope and intercept, or whatever weight terms are, so that this function that calculates the differences between the actual data values and our line is minimized. Okay. You have seen, I presume, whether in 102A or another class, you have seen different kinds of optimization algorithms. So in 102A, one of the optimization algorithms we covered was coordinate descent. We also had Nelder-Mead. In this class, we're going to look at gradient descent, which is another optimization algorithm. It's a numeric method, kind of this iterative process, and eventually it gets you to what we expect to be a local min, local max, possibly a saddle point. Okay. So if you think about a function of one variable, single variable function, univariate function, the derivative represents the slope of the tangent line to that graph at some point x. If you have a function, a multivariate function, okay, then the gradient is the direction of greatest increase of the function at some location x, okay? And then the magnitude of the gradient is the rate of increase in that direction. And the idea for gradient descent is that if we are located at some place, we use the gradient. The gradient is going to point in the direction of greatest increase. So the gradient always kind of points uphill. And all we do is we move opposite of that direction. Okay, so if you say that's uphill, I'm going to take a step backwards from uphill. And if I take a step backwards from uphill, I'm going downhill. Okay, and if we repeat this process, okay, of continuing to take steps backwards from uphill, then I will continue to go downhill, and that will eventually, if I'm always making sure I'm going downhill, eventually we'll reach basically the bottom of our hill, okay, or at least the bottom of some kind of valley. And so the gradient descent algorithm is really, 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 really simple. It's basically just one line here, okay? We have some multi-dimensional function. This is basically our loss function. The input is our vector W, the different weights. So if it's linear regression, W is our slope and intercept. If it's something more complicated, it's all of the different weights, different parameters that we're trying to figure out, okay? The output of this function is a single scalar value, basically the mean squared error or the sum of squared errors, or whatever it might be, okay? And so the gradient descent algorithm is iterative. You start at some arbitrary location, W at time n, that's what W sub n is, and then what we're gonna do is, based on our current location, we wanna find the value at the next iteration. So that's going to be W at time n plus 1. So W n plus 1. And the way we find it is we just take our current location, W at time n, and we subtract off some scalar value, positive scalar constant, times the gradient, nabla f, times the gradient of f at our current location, W sub n. Okay? So we're just saying at the next iteration, so gradient descent is an iterative algorithm. We're saying if you're currently located here, okay, take your current location, find the gradient at your current location, and take a step in the opposite direction. So you take your current location, subtract off, so your gradient's going to point, as a little vector pointing in a certain direction, and we're saying subtract that, so we're just going a little bit in the opposite direction. That's all it's saying, okay? And then that will update your new location. Now you have a new location. You calculate the gradient there. Take a step backwards, okay? And you get a new location. So basically, if you have some kind of three-dimensional surface, okay? So this is like some kind of parabolic dish here, okay? And you have some location right here. The gradient is going to point is going to be some vector that points in this direction, right? And then you just take a step opposite of that, okay? And so you end up going kind of down here. And then now you have a new location. You calculate the gradient there. It points in this direction, and you take a step down from there, okay? And then you get another gradient, and you just keep repeating this process, and you keep taking little steps downhill, because the gradient just keeps kind of pointing up, and you just keep taking steps in the opposite direction. And that's it. Current location, W at time n, subtract off the gradient at W at time n, and that will give you W at time n plus 1. And then you just repeat. So it's just a one-line algorithm. So what does this look like? Okay. So here we're going to do gradient descent on some kind of arbitrary function. This is a function of the input is two-dimensional. We have a function of x. So instead of w, I just put function x. I've got x1, x2. And this is x1 squared minus 2x1 minus 0.5 x1, x2 plus 2.5 x2 squared. And it's basically some kind of parabolic thing that looks like this. And so we can find the gradient using calculus, okay? So I'm going to kind of just do partial derivatives. So remember, the definition of the gradient is the vector of partial derivatives. So I've got the partial derivative of f with respect to x1, and I have the partial derivative of f with respect to x2. So if I take what is the partial derivative of this thing with respect to x1, here I'm going to get 2x1 minus 2 minus 0.5 times x2, okay? There's no x1 term here, so this zeroes out. So that's the first partial derivative, 2x1 minus 2 minus 0.5x2. Okay, now I want to take the derivative, partial derivative of this with respect to x2. And so there's no x2 here, so that zeroes out. This zeroes out. I'm going to get minus 0.5x1. And then here I get 5x2 for the partial derivative with respect to x2. So now I have a vector where the first component is the partial derivative with respect to x1, and the second component is the partial derivative with respect to x2. Okay, and so this is my gradient. So far, so good. Okay, and normally what we would do is we would set this equal to 0. We would have two equations, two unknowns, and we would solve for x1 and x2. But we're not going to do that. We are going to use gradient descent and take an iterative approach so that we start at some arbitrary location, keep applying our gradient descent algorithm, and eventually that should get us to some location that is close to what we would have gotten if we set this equal to 0 and solved. Okay. Let me go ahead and give you your first view quiz answer, which is the letter A. A as an apple. A as an apple. Okay. So again, traditional approach, you'd set this equal to 0 and solve, but we are doing a iterative numeric calculation approach. So this is a contour plot of this function here. And so just kind of looking at it, so again, the contour plot is, if you have this kind of parabolic thing, you got, and you drew, I don't know if this picture looks right, but you drew kind of these horizontal lines of latitude or whatever of equal height here, and you take and you look down from the top. What does it look down? It's basically going to look like a whole bunch of concentric rings, kind of like that, okay? And that's what we see. And so the minimum is going to be located around here. I don't know where that is, 1, 0, I don't know. Something like that. It's located somewhere around here. We're going to start at some arbitrary location. Here's a 3D plot of what this looks like. So if you were to chop, fit this into a cube, it would look kind of like that. And so the bottom is somewhere around there. And so we're going to just say, let's begin at some arbitrary location, -5, 4. So I guess that would be like right up here, this corner up here. -5, 4. And so we're going to calculate the gradient at -5, 4. So at -5, 4, remember my gradient is this vector of our two partial derivatives. So I got 2x1 minus 2 minus 0.5x2. I plug in -5 and 4 for x1 and x2. So what is this? 2 times -5 is -10. Minus 2 minus 0.5 times 4, so minus another 2. That gives me -14. Over here for the partial derivative with respect to x2, I have 0.5x1 plus 5x2. So what do we have? I get -0.5 times -5 and 5 times 4. So that's 20. And this is positive 2.5, so I get 22.5. Just a heads up for your midterm exam, which is, I guess it's just 2 weeks away or whatever, but it's welcome to the quarter system. I will probably ask you to do some calculations of gradients, and it always breaks my heart when a student kind of starts off their work correct, but then like messes up multiplying -5 times -0.5 and leaves it, negative times negative becomes a positive, and they leave it at -2.5, and then it throws this off, and then like everything else gets thrown off, and it's like really hard to grade like that, and the student ends up losing points, a bunch of points and stuff. So just be careful with your math as far as multiplying numbers together and adding them together. So punch it into the calculator and double check. Okay. So this is our gradient. So at -5, 4, this is our gradient. And so remember, the algorithm is basically take your current location, okay, here it's -5, 4, and subtract off a small positive constant or just positive constant times the gradient at that location to give you your next location. So here, I'm going to just use a step size of 0.1. So, so my current location is -5, 4. My gradient at that location is -14, 22.5. And I'm going to do -0.1. So I'm going to do this, right? So when I do -0.1 times -14, I get positive 1.4. -0.1 times 22.5 gives me -2.25. -5 plus 1.4 gives me -3.6. And 4 minus 2.25 gives me 1.75. So the location at my next iteration is going to be -3.6, 1.75. And I'm going to plot this so you can see what this looks like. Okay, oh, here it is on the computer. So I have a function saying if you take in x1 and x2, this is the output, x squared minus 2x1 minus 0.5 x1 times x2 plus 2.5 x2 squared. And then we're finding the partial df dx1 and the partial df dx2, and then we're returning a vector with those two things together. Okay, and so if I plug in the same thing, -5, 4, my gradient is -14, 22.5, and my next iteration, which is my starting location minus gamma, which is 0.1, times the gradient at that location, I get -3.6, 1.75, which matches our calculations by hand. Okay, and so here it is. This is our plot. So here's our starting location, -5, 4. And after we take one iteration, you can see this thing points downhill, okay? And so at this location, the direction of steepest descent is in the opposite direction of the red arrow. Flip that around. And what we've done is we've taken a step in the opposite of the gradient, which points downhill. Okay, and that's what we have. Okay, does that kind of make sense? So now this is my next location. This is -3.6, positive 1.75. You can see that is the coordinate here. -3.6, 1.75. That's this location. And that's going to be my next thing. I plug in -3.6, 1.75. If I plug that into our formula for what is the partial derivative of with respect to x1 and the partial with respect to x2, I get my gradient of -10.0.075, 10.55. Okay, and what we want to do is we want to take -3.6, 1.75. That's my start location here. Minus 0.1 times 0.1 times the gradient here. Okay, so 0.1 times -10.075 is going to, -0.1 times -10.075 is going to become what? Positive 1.0075. So -3.6 plus positive 1.0075 gives me -2.5925. And then here I have 1.75 minus 1.055. So 1.75 minus 1.055 gives me 0.6950. And if I plot that, that takes me to my next iteration. So my next stop is going to be -2.59, positive 0.695. So -2.59, positive 0.695. That's right here. And so from this location, this would have been uphill, and we're moving opposite of that, and that takes me downhill. And that's this thing. Okay, and I can repeat this process. I can say for I in 1 through 20, okay, calculate or store our current location into locations row I, and then calculate the next location, which is going to be our current location minus gamma times the gradient, and then store that in locations I here, and then here we're going to plot, okay, plot from rows 1 through 19. because what we're going to do is we're going to take the starting location at row I, coordinates 1 and 2, and then we're going to plot it to row I plus 1, coordinates 1 and 2. So because when you plot an arrow, you need the starting xy coordinate and you need the ending xy coordinate. So here it's just going to go 1 through 19 because I only have 20 rows in my table. So if I say 1 through 20, I'll end up at the 20th and it'll say, hey, where's row 21? And we're not going to find that, right? So we got this, okay? And this is what it looks like. I start off at -5, 4. I took a step downhill and I ended up here. Then I calculated the gradient, went in the opposite direction. I ended up over here. Calculate the gradient, go in the opposite direction. I end up over here. And continue and continue and continue. And we can see eventually, as I'm going downhill, I end up towards the center, okay? As I get farther down, the curvature gets more and more shallow, right? The walls of the bowl are no longer as steep. And the gradient, the magnitude of the gradient is basically a measure of how steep those sides are, okay? So in the beginning, we're taking big steps, but as we get closer towards the bottom, we take smaller and smaller steps because my gradient gets smaller and smaller. It's the slope is no longer as steep, so my gradient gets smaller, and so my step sizes get smaller and smaller. So when you do gradient descent, you never actually reach the very end. You have to, it's kind of like, I don't know, any of those kind of paradoxes where if you take, if I travel half the way, the distance to that wall, and then I take another halfway to the distance and halfway to that distance and halfway to that distance, I get closer and closer and closer to that end, but I never actually reach it, right? And that's basically what's happening here, because at the very bottom, my gradient is 0. And if my gradient is 0, then I'm not going to be taking a step size. So, but you can see it's tending towards the very end. So with gradient descent, you can just kind of let it run even more than 20 iterations, 1,000 iterations or whatever, and towards the end, you're getting really, really tiny step sizes, maybe even hitting the limits of your floating point arithmetic. But it'll get you pretty close to the bottom, right? And that's the goal of all numeric methods. Is we're not going for analytic solutions. We're just trying to look for something pretty close to the final answer there. Okay, you can adjust your gamma. Okay, so remember, gamma is this constant that we multiply in our algorithm here. So in our algorithm, we take our current location minus gamma times f. Gamma is some scaling factor. Over here, it was 0.1. Okay, I could shrink it to say 0.03. And what happens there? Now my steps are even smaller. Okay, so this first step with 0.1, I took a step this big, and then my next iteration, I took a step this big. Here with a gamma of 0.03, my first step is basically 30% of that original step. Then the next step is that, the next step is that. And so after 20 iterations, I'm only this far. So it's going to take me a whole bunch more iterations to really get to the bottom, okay? Here's a bigger thing, steps gamma of 0.15. So I take a big step, then a big step, then a big step, and I get, the thing of the step size is still shrinking because the gradient is shrinking. That still happens, but I get converged towards the center faster. But if you push gamma too big, you get kind of this little back and forth effect. So what happened here is it said, we need to go that way. And then so you take a big step that way, and you're like, oh no, too far, too far. Okay, go, turn back, okay? So this is what I call adjusting the temperature in the shower, right? It's too cold, so you say, oh, I want it hotter, and you turn the knob that way, and you're like, oh, too hot, and then and then you got to go back, right? So these are like the two different approaches for adjusting the temperature in the shower. One is you can just try to just like tap the thing ever so slightly until it gets to the right temperature, or you can say, oh, it's too hot, and then go this way. Or, I mean, too cold, so you go this way. Now it's too hot, and you got to go kind of back and forth, and eventually you dial it in. Okay. If you do it too much, you can just end up going kind of like wildly recklessly. This is, I don't know if you've seen like somebody like fishtail their car, and it's like they try to overcorrect their car, and eventually just they flip the car over and stuff. But this this could also happen if you have a big gamma. Okay. Now at this point, basically, so if you imagine the like the side view of the parabola, kind of like this. I don't know if this is even worth trying to capture here. So here it says take a direction. This is going that. Take a direction, the opposite direction, and when you go in the opposite direction, you end up actually over on the opposite side. So ideally, you kind of go down the hill like this. Step, 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 step. But here you say go in the opposite direction, which is this way, and you end up actually on a steeper side, on the opposite side, but on the steeper side. Okay, it's even steeper. And so now the magnitude is even more in this, and then so now you end up over here, and then you end up kind of just shooting back and forth, and then so it ends up diverging. Okay, so that could happen too. So how do we choose our gamma? Well, we don't have a good answer for that. Okay, choosing what gamma you want to use really feels kind of arbitrary. This is an area of active research, and there are algorithms that have been kind of tuned to do this, but this is still a thing. Like with neural networks and whatnot, you will see kind of these cost graphs that kind of go down and then suddenly go wild and things like that. And that's because figuring out exactly what learning rate, what gamma you should use is a little bit tricky. Okay, there's kind of a lot of trial and error. The general strategy: start off small and then keep increasing it until because bigger means faster convergence, but too big means it's going to diverge and not converge. Okay, but too small is going to take like way too many iterations to get there. Okay, so general's recommendation is start small. If it looks stable and working, then you bump it up, and you try to keep bumping it up until so that you can still converge, but it doesn't explode, because you want it to go a little bit faster, but you don't want it to break. Okay, so there are different algorithms. We're not going to cover them. They're a little bit beyond the scope of this class. One of them is called Atom. There's other things. Okay. All right, let's go ahead and try using gradient descent as a way to solve for the slope and intercept in ordinary least squares. Okay, let me give you your second view quiz answer, which is the letter B. The letter B is your second view quiz answer. And so we're going to use gradient descent and apply it to ordinary least squares regression. Okay, so ordinary least squares regression, we're trying to minimize the sum of squared residuals, or the mean squared error, which we've written as T minus XW transpose, T minus XW. It's the equivalent to this, right? I guess times 1 over n. So we can do this. We can find the gradient analytically. I can find the partial derivative with respect to W0. I can find the partial derivative with respect to W1. And we can do it that way. Or we can find the gradient with respect to the vector W using matrix notation. Okay, and that's what we're going to do. Okay, we're going to use matrix notation to find our gradient. All right, so we have found the gradient analytically, no problem. And what we did say, I think on Friday of last week is, or was it Wednesday of last week? We set this thing equal to 0 and we solved for W to find what is the solution of W that's going to minimize or have a gradient equal to 0 and therefore minimize the loss function, sum of squared residuals. But here we're going to use gradient descent. We found the gradient, but we're not going to solve for W analytically. We're going to take an iterative approach. So this is what this is what our gradient descent algorithm looks like. We have our starting location at, or arbitrary starting location at time n, and we say what is it going to be at time n plus 1. We take our current location and we subtract off gamma times the gradient. Okay, where the gradient nabla f is equal to this thing right here. Okay, so just to put a step back and understand the big picture, okay? It is a little bit silly to do this for linear regression because linear regression is already a solved problem, right? We know exactly how to find the slope and intercept that minimizes the mean squared error, okay? And we can do that in R just using LM. And so here I have this very, very, very simple, tiny little data set. My x values are 1, 3, and 5. And then my y values are okay, so if this is 2, 4, 6, 8, 10, 14, 18, we're at 4.8, which is going to be right around here. And then 11.3, 11.3, which is going to be somewhere around here. And then 5, 17.2, which is going to be somewhere around here. Now we're trying to find what is the slope and intercept that's going to best fit my data points here. Okay, this is what we have. And the answer is you need an intercept of 1.8 and a slope of 3.1. Okay, sure. And if you plot that intercept of 1.8 and slope 3.1, this is the solution. And you look at that and you go, yeah, that seems to look like a line that's going to fit our 3 data points. Can you see these data points right here? There's a dot right there and a dot right there. Okay, so you say, oh yeah, that makes sense. This is a line that's going to minimize our mean squared error. Okay, but again, what we're going to do is we are going to do gradient descent. So here is the equation of the gradient, negative 2 over n x transpose t plus 2 over n x transpose x w. This is the gradient of our loss function with respect to w. Now, I have this constant 2 over n over these things, but remember, we're going to take our vector w at time n and minus gamma times f here at wn, right? And so, you know, this part has basically a 2 over n, and I can just, you know, have some, you know, gamma times 2 over n is basically another constant, okay? So I'm going to just drop the 2 over n here, okay? And I'm going to just plug in matrix notation, basically x transpose negative x transpose t plus x transpose xw. Okay, that's my gradient. And so here I apply the algorithm. It's just a one-line algorithm. I'm going to start off an arbitrary location at negative 1, comma 1.5. I use a gamma of 0.02, and then I just say, let's run this 1,000 times. I'm going to take my current w vector, subtract off gamma times the gradient, which calculates this thing, okay? And I just repeat this one line 1,000 times. And at the end of it, it says, okay, the vector that I calculated was 1.79995, and the slope, I'm sorry, the intercept was 1.79995, and the intercept is 3.100001, okay? Which is pretty close to the formal solution found by using LM of 1.8 and 3.1, okay? Again, this is a numeric method, and the goal of numeric methods isn't to get the exact answer, but to get us pretty close to the real answer. And I think we have succeeded in doing that, okay? Let me just kind of show you what this looks like, okay? So remember, the minimum occurs when the intercept is 1.8 and the slope is 3.1, okay? Here I'm plotting these things. What does this plot represent? This represents the contours of your loss function, okay? So let me, so on the horizontal axis, I have different values of the intercept, and on the vertical axis, I have different values of the slope, okay? So let's say you had a line that looked like this, okay? So this is one possible combination of slope and intercept. And your loss would be the sum of squared errors. What is the difference between the line and the dot? What is the difference between the line and the dot here? And what's the difference between the line and the dot? So you have these, very big sum of squared errors, okay? I could just imagine, I guess, a knob where I can change the intercept, okay? And I could just take this line and I could slide it down, okay? So I'm going to keep the same slope, but I'm going to slide it down now to here, okay? I wish I had a different color. So now, what is my sum of squared residuals? It's going to be, this is my residual, and this is my squared residual. Here's my residual, there's my squared residual, here's my residual, and there's my squared residual. So what's the sum of these squares? It's something different, right? And so we can, there is a website. Okay, so here is, this has more than 3 points, but this knob is going to change where the intercept goes, okay? It's just going to slide the line up and down. And so here I can have the line go through the red and blue dots, and I have no corresponding residuals corresponding to the red and blue dots, okay? But I've got pretty big residuals for the green and orange dots here. I could slide the line up to shrink the residuals for the green and orange dots, but now I have bigger residuals for the blue and red dots, and so on and so forth. And so I could pick different values of the intercept, and the sum of the squares residuals will change. And this plot right here represents what is the, this shows the contour of the loss function that says, hey, if you picked an intercept of 0, if you kept your slope constant at 2 and an intercept of 0, this is what your thing is. As you slide your intercept higher, and kept the constants different, then the amount of error changes. And so, let's just take a look at this. So here I began with an intercept of -1 and a slope of 1.5. Okay, the true line has a slope of 3.1. So our line is way too shallow, right? So we have huge residuals between this, the actual and the predicted. Actual and predicted, very far different, okay? And so the gradient says, you know what, if we do gradient descent, it says the first thing you gotta do is you gotta push that slope up much higher, okay? And so at the next iteration, we have a steeper slope, okay? And we can see, yeah, this second iteration this does a better job than this one of fitting our data. It doesn't do a good job, but it does a better job. And so the residuals between the actual and the predicted line are smaller. And that's here, okay? It says you still got to make it steeper, okay? And so after a few more iterations, we're up to here, okay? And so now my slope is, what, 3.2 or whatever, okay? But my intercept is a little bit off, so, but now I have different size residuals, okay? After more iterations, we're right here, okay? And so we can see, compared to the actual line, maybe my slope is a little too steep now, okay? My slope is a little too steep, okay? I've got much better kind of performance here, and you can see in the contour lines out here, when I was down here, my sum of mean squared error was like 100, and each of these things, you know, dropped down to 80, 60, 40, 20, 10, and now we're just kind of, we've approached a much more flatter region. If you look at the contour plots, we're going from like 5 to 4 to 3 to 2. So, you know, making these adjustments is just kind of fine tuning this, okay? And so now I'm a little bit too steep, and so what I need to do is I'm going to actually lower the slope so it's not as steep, but I'm going to increase the intercept, okay? And so you're going to see the slope come down a little bit, but the intercept climb up, okay? And so you can see the line kind of, so we started off with a too shallow, we got too steep, and now I'm going to try to fine tune it by bringing it down like this, okay? The slope comes down, the intercept comes up a little bit, and so it took me 300 iterations to kind of get to here, okay? And it's still not a great answer, but we're starting to do better, right? We're starting to do better with kind of the right amount of slope and the right size intercept, okay? And that's basically that. This is just showing you like what happens if your gamma was too big, and again, this is kind of the hot water situation where you bounce around a little too much. Here, we're still able to do it. Here, this just kind of goes much too big and goes wildly off and things like that, okay? I've run out of time to do this numeric gradient calculation and checking. The idea here is, what if you could not find the gradient analytically with calculus? What can you do? You can calculate it kind of manually, numerically, by just adding on a tiny little delta, like a 0.01 or 10 to the minus 5, okay? The important thing here is you have to remember the gradient is a partial derivative with is a vector with two components. One is the partial derivative with respect to x1, and the other is partial derivative with respect to x2, or if you have more things, partial derivative with respect to x3 and x4 and so on and so forth. When you calculate the partial derivative with respect to x1, you add the small little h only to the x1 component, and you leave the x2 alone. When you find the partial derivative, when you're estimating the partial derivative with respect to x2, you add the h only to the x2 component, and you leave the x1 alone. Okay, so here, I calculate my baseline starting point. What is it at -5, 4? It's 85 is my loss function. Then I'm going to say, all right, let's add a tiny little like 0.01 to this. When you add 0.01 just to the x1 component, it goes from -5 to -4.99. How does that change the value of your loss function? Well, when you plug in -4.99 instead of -5, okay, and you leave x2 alone at 4, you get 84.8601, okay? How much did that change from 85? It changed by a factor of by 0.1399. You divide by the size of that little increment, so you get a -13.99. You do the same thing on x2. You leave x1 alone at -5. You change 4 to 4.01. How does that change your loss function? When you plug it into all of this and you plug in 4.01 instead of 4, you get 85.225. So a difference of 0.225. Okay, you divide that by 0.01 and you get 22.525. So your estimated gradient, if you could not calculate the gradient analytically, your estimated gradient is -13.99 and 22.525. You can compare that to the analytic gradient, which is negative 14 and 22.5. So kind of close, not exactly the same. Okay, we'll go ahead and wrap things up here. And for those in person, I will give you your final view quiz answer.